Hey, this is Nick Richard with Radwave, and today I'm here to talk about the Breakthrough Listen project and kind of my take on what it is and how to really dig into it. Breakthrough Listen is a scientific research program. So it started back in 2015, 2016 timeframe, um, and they're using some of the most exquisite hardware on the planet in order to listen and search for techno signatures coming from deep space. And one of the most exciting aspects of this program is that it's the first time I'm aware of where there's data that's been made publicly available. So here on the Open Data Archive, the data itself comes from either the Green Bank Telescope, Automated Planet Finder, or Parks, which we'll dig into in a moment. And they have the baseband data. So this is the raw data that can come right off of these telescopes. And the data volume is absolutely enormous. So there's 2 petabytes of data that's been made available to the public. As you can see here, we have just a huge amount of files, and each one of these is about 17 gigs. So just an enormous volume of data that's been made available to everyone to look at, which historically has never been done. And the goal here, when I had read this, back in 2016, the thing that really caught my attention is that the person who's funding it, Yuri Milner, really wanted to bring a new way to doing radio astronomy and the search for extraterrestrial intelligence. So specifically, you want to make this data transparent. You wanted to enable innovation, and you wanted to enable the data to be crowdsourced. So leveraging all the people that we have here on the planet to actually help in this endeavor. And that's a really critical thing because historically the community that does radio astronomy or radio signal processing in general is quite small. You really have to have a highly technical background. But the community of people who are interested in space is absolutely enormous. Basically, anyone who's looked at the sky, if you've seen it on a dark night and looked up at the stars, it's unbelievable. Just how enormous it all is and how much possibility there is. And so it's just really, really cool that this data has been made available. But as of today, so this is 2024, we're about 8 years into this program, and there just hasn't been a lot of people outside of the traditional SETI community that have been able to leverage this data because it's in this really highly technical data format. It's absolutely enormous. So it just becomes a big burden for anyone who wants to tinker with it. Now, in 2016, I developed a different way of storing spectrograms, which are really critical when it comes to radio signal processing. And we'll dig into that later in this talk as well. But it struck me at the time that what I came up with was directly applicable to this particular project, which was extremely exciting for me. And so I've spent a number of years tweaking this and tuning it and refining it and getting to the point where it's ready for some alpha testers. And I've made it now in a way that I've been able to decentralize the processing, decentralize the storage in order to alleviate all the financial burdens of doing this work, because 2 petabytes of data is nothing to sneeze at. So in this talk, what I want to take you through is kind of how to even get started. But the data that's available here, the only thing you can do is download the files, and this downloads a raw file. While there is some information here about how one might be able to process this, there's no just easy to use software that's come from the people maintaining this tool, because it's so technical. But that is what I'm hoping to bring to the table with Radwave. It's a tool that anyone can just double click, open, and it'll handle all the burdensome processing that computers are very good at, and enable people who are really good at just seeing and observing unique things that haven't been seen before. So that way it can be labeled and shared with the greater community. So back in 2019, I was able to produce my first Android application for doing this type of processing with this type of data. The basic process is that we have, some antenna that hooks up to some computer in order to get the digitized data from the antenna itself. But that data is in that highly technical format. And so at the time, what I was doing is all the Radwave processing was happening in the cloud. So it could be accessed at scale, where you have this, binary data that goes into the cloud, and this much more easily digestible data comes out. And as such, the client application that you run on a Android smartphone would allow you to pan and zoom through that spectrum interactively and intuitively. So that way you could tag stuff and share it with people. So this app is available on the Google Play Store. It may still work. It's been a few years since I've been able to maintain it. But you can hook up an RTL SDR to it, or you can look at data from the Green Bank telescope, which is there now. But in order to just have a basic understanding of what's in there, I wanted to just overview what exactly a spectrogram is, so that way you can help interpret it. So if you just watch and listen to this. So what we can see here is we have this is me whistling, is what it is. And so the horizontal axis is frequency, and the vertical axis is time. And the color here is indicating how much energy was at a certain frequency at a certain time. So where it's red up here, this corresponds to about 700 hertz. And then you could hear me whistling at lower and lower frequencies. And this spectrogram is showing you basically a profile of that sound. And the same exact approach for audio can be done for radio. So for radio, instead of having a microphone for audio, we have an antenna for radio. And we can digitize signals with the exact same approach, just at a much higher frequency. So here we're going from DC, which is 0 hertz, up to 2800 hertz. With radio, you're going also from DC, but up to gigahertz ranges. So just a much, much wider bandwidth. Now, for other types of signals, they're going to have different types of spectrogram profiles. Yeah, so here you can hear a car engine, a race car engine, and we can see all these harmonics that kind of come through the spectrum. You can see that they're spaced out, and as the car is going faster and faster, that engine is revving faster and faster. The RPMs go higher and higher. The the frequencies that you hear also go higher and higher, right? Because they're directly related to that mechanical interface. With radio, we have the exact same phenomena happening. So there's all sorts of things that vibrate, whether they're on atomic or molecular scales to celestial scales, where you have like entire suns emitting lots and lots and lots of radiation. And they're emitting radiation not just in the visible band and the infrared band, which is heat and light, and ultraviolet, which gives us a sunburn, but the entire range of the electromagnetic spectrum, all the way from radio, all the way through X-rays and beyond. So all of these audio examples are really intuitive and easy to understand. And we you can envision all different types of phenomena that have these different spectrogram profiles. The question is, how do we take these concepts and apply it to the Breakthrough Listen data? So let's go back to the Open Data Archive here for a moment and try to better understand this. So, and first what we're going to do is just try to understand, what data is even included in these, like, what does this mean? And is there any other information that we're going to need to be able to make sense of it? So what Breakthrough Listen is doing is they're using the Green Bank telescope, which is this large single dish antenna that's located in Green Bank, West Virginia. Green Bank, West Virginia happens to be located in the National Radio Quiet Zone. So the surrounding area around this telescope has much more limited radio emissions. So that way, this isn't being drowned out by man-made interference. So the GPT here for the project, that stands for Green Bank Telescope. So this project column here, that simply corresponds to which of these sensors effectively is being used. The next one here is the target. So this antenna is pointed at different parts of the sky in order to observe different targets that are of interest to the SETI community and radio astronomy community in general. I don't know these nearly as well as the technical engineering details of processing the baseband data. That being said, if the SETI community finds them important, I'm sure there are. For this one in particular, I have looked into it a little bit, and it's a triple star system that has an exoplanet within it, which is pretty cool. RA stands for right ascension, and declination goes along with it. So these correspond to the pointing angles of the antenna at the time that it collected it. The time of the collection here is UTC. So this is when the observation started. And MJD is modifying Julian date. So this is just another way to state what time it is. And modified Julian date is used more by the astronomy community than UTC is. The next most important thing, or one of the most important things, is the center frequency. So when you're doing audio, our ears are only able to hear between 0 hertz and 20 kilohertz, so 20,000 hertz. And that's the fixed range that we can hear. Radio is slightly different, where it has a bandwidth that it can listen to. So the bandwidth of audio for humans is 20 kilohertz. That's the widest we can hear. radio can hear wider in general. But not just that, it can also hear at a different range of frequencies. So you can shift that up and down in the spectrum. And so the center frequency for this data is 2157 megahertz, so million hertz. And all of the baseband data files are 187.5 megahertz wide. So if you take that 187.5 megahertz, divide that by 2, that's going to be like 90 some odd megahertz. So this will be going from this. If you take that center frequency, subtract 90 megahertz on one side, add 90 megahertz on the other side, that's going to be your effective range of frequencies that you're observing at that time. And so that can be slid up and down. So we can see here that there's a range of different frequencies that it's centered on, but it's observing different portions of the spectrum. And we'll be able to see that in more detail as we get into the Radwave app itself. Okay. We also get the file size. This is about 17 gigs, and then we have a download link in an MD5 sum. So this is in order to verify that the file has the contents that was noted by the scientists who collected it. So the one thing you might observe here is that we have these 2 rows of data where the only thing different is the MD5 sum. So the UTC time is the same. The modified Julian date is the same. The target is the right ascension declination. The center frequency is the same. It's the same type of data, but these are 2 different files. And so one of the things that's a little bit confusing with this data is, well, what is actually different about these 2 files? And so the way that time is recorded in the files is slightly different than normal. And the only way to see it when you're looking at the Open Data Archive is if you see at the very bottom of the screen, way down here at the bottom, the scan number in the file and the file number, those can change. And so you really have to kind of keep close track if you were to just use this interface. In Radwave, I help address that to make it more intuitive what files actually go together in time. So now that we have a basic understanding of, what these columns stand for, the other thing is, just how much data do we really have here? So if we just do a search for all the Green Bank Telescope baseband data, we see that there are 50 pages of results with 20 results per page. One thing I found on this, let's say if we just try to look at 100 files at a time, we still get 50 pages of results. So this actually points to potentially a bug in the implementation of the database here, is that I think they're limiting the results by accident. And so if you change the URL to search for page 51, you'll still get a 51st page. And there ends up being something on the order of 400 some odd pages of results. Maybe it's 420 something. I can't quite remember the exact number. But in order to really understand the full scope of data that's been made available, we really need to automate this process of querying this data, finding the right times, understanding what frequencies are there, find the right times, understand the frequencies, understand the targets, and understand the full range of data that's been made available so that we can leverage it all. I've open sourced this metadata scraper that I put together in order to do this job. So this has 3 different scripts. there's scrape BTL open data. So what this is doing is scraping the data straight out of this table and recording that all to a CSV file. But then in order to resolve the time, so that's the main thing that we don't really have precise knowledge on, just looking at these, what's presented in this table itself. What we have to do is download the first header from each of these files. So the way these files are structured is, so the very first part of the file contains a header in it, which contains additional metadata that isn't provided in this table. And then we have the raw data from the telescope. All of that information is detailed in one of the papers that was released by the Breakthrough Listen team. So here they've got all sorts of just phenomenal details about how all of this works. And so what we're going to do is not download the entire file. So we simply can't do that for 2 petabytes, but just that first, 6 kilobytes per file will give us enough of the header information, enough of the metadata that we can resolve the time discrepancy here. And lastly, what we do is then validate those headers that we've downloaded, just to make sure that all the critical fields are correct, getting those precise times. And I'm not completely sure if the precise times are correct, but from what I can tell, it looks close enough to make it work. So let's dig into the code a little bit so you can better understand what's going on. So for the scrape BTL open data, I have some details about it here. But essentially all we're doing is just going to this URL, using these parameters to get pages of table results. And then we're just parsing out the data between the HTML table row tags. So once that's been done, all the results are put into this ODA CSV file, which we can see here. So just like what you had, it's the UTC time, the MJD time, telescope, object, right ascension, declination, center frequency, file type, size bytes, MD5 sum, and download link. So let's let this format. So here we can start to get a much better idea as to what all is available. Now the code to download the Guppy headers, here it's reading that ODA CSV file, and then it's doing a range request for the download link, right? So this here is where each of these paths is located. And we only need the first about 6 kilobytes in order to get that first Guppy header. And then once we get the Guppy header, we can, assuming there's no issue downloading it, we can find where the end of the header exists. So we get the header length, which can vary a little bit because some of the files were recorded with slightly different metadata. Decode it. It's all just ASCII text for the header fields. Get the names, create that dictionary, and then what this step here is doing is taking all the additional metadata that was found in the Guppy header and adding it to this CSV and then saving it as a new one. And so that produces this file here. So this might take a moment to align the columns, just because this is starting to get fairly bloated. All right. So here we see our original columns from the Open Data Archive webpage. And here, with all they have to be capitalized, are all the different metadata fields from the Guppy header. So some of them are kind of duplicative from what's in the table, which is good. But there's a lot of things here that are new. And since we're most interested in the time, you can see there's nothing here that has a precise time. So you can go ahead and look at the details yourself, but nothing here tells you with granularity of more than about 1 second what the time of the samples is, and which is slightly atypical for digital signal processing data sets. When you're doing collection at these data rates, you often will have at least a counter that will increment at the sample rate. So with audio, let's say you have like an audio CD, so it's 44.1 kilohertz. So you'll get a sample every 1/44,000 seconds. Here we're at 187 megahertz. We'll get in details because it's sampled in a channelized fashion. But we should have timestamps that are accurate and precise, that are in the microsecond range at a maximum. Really, it should be much less than that. But just looking at the metadata itself, you can't really find any field that has that level of precision. And so in the validate Guppy file, what we're trying to do, a major part of this is trying to determine what fields we may be able to use to construct that precise time. And so what I found, and I'm not sure if it's perfect, so anyone's welcome to correct me, is there is a field called which is the packet index, and then there's the packet size. We also have the number of bits per sample, and the number of polarizations. And with all of that, we can obtain a sample offset. From what I can tell, that sample offset is relative to the start of collection time, which would be your modified Julian date, which is the integer portion, the seconds portion, the offsets portion. This, from all the data I've looked at, results in an integer number of seconds and as a modified Julian date time. And then this start time offset will give us the offset from that start of collection time to where the actual file begins for that particular Guppy file. And so with all those things together, we now, in this valid ODA headers, we have not just what was provided from the Guppy headers, but also this start UTC, which has resolution on the order of microseconds, which is what we really need in order to stitch these different files together. But with Radwave, what I've done is I've taken all of this information and I've included it in the Radwave engine. So that way you can more easily see what's there. So what we have here on the left is a list of all the targets that are from the Green Bank telescope that have baseband data. I'm limiting myself to that right now because the Parks data is in a slightly different format. I just haven't had a chance to comb through it in as much detail yet. But if we click here on TIC 159.107.668, this is just a random target I found that has a, it's just easy to see what data is available for it. Not too much, not too little. This is a kind of an abstract spectrogram plot. So here we have time on the vertical axis, we have frequency on the horizontal axis, just like when we were looking at me whistling and the car engine. And then here on the bottom, we have table where you can see different details of each of these different files. So each blue box here with a red border corresponds to one Guppy file. If we use control click, right? So if you use control click, you can select one that's going to add it to a collection that you would process here. You can see that the amount of space you're going to need to have on your hard drive is 17 gigs for this one particular file. But when it gets pre-processed, the engine will do pre-processing, so that way we can later explore it interactively. That data is going to get inflated, especially if we enable audio output. Additionally, Radwave, the engine provides information about your disk capacity and your disk space, so that way you can be cognizant and not accidentally saturate your hard drive and bring your computer to a halt. We want to avoid that at all costs. If you want to purely download the files so that way you can analyze them yourself, welcome to do that, and just use this as a more convenient means to download files that are at adjacent times in the same frequency, which is kind of hard to do from the Open Data Archive user interface. But regardless, at this point here, if I want to enable my audio output, I can start the download and process, and just let you know, this is going to take a while to run. It's doing a lot of heavy lifting here in the process, and is limited by both the amount of RAM that you have available, your network download speed, and your the speed of your hard drive. So I'm going to stop this for the time being, so that way I don't fill it up necessarily. All right. So this is about all we have time for today. We can dig a lot more into, how the files are arranged within the Breakthrough Listen servers, so that we understand, what our constraints are for downloading this volume from these particular servers, as well as how to view the spectrogram within the Radwave Explorer once we've actually gone through a full collection. All right. Thank you so much for your time today. I really appreciate it. Any feedback is extremely welcome. And alpha testers are more than welcome to join up. All you have to do is subscribe to the Radwave blog here. And there's a whole bunch of details about this, along with some tutorials about the Radwave engine here and the Radwave Explorer here. So feel free to take a look at all the juicy details and join us on Discord, so that way you can let me know if there are any sort of hiccups. I'm extremely excited to work with you guys. Thanks. Bye.